Good morning, everyone. Good to see you all in this Friday lecture, Friday class. So welcome to lecture 14 of 124103. This will be the third and last lecture on fluids. Next week we'll go to a different topic. So I'll just give sort of a recap. We started talking. Oh yeah, before I begin, just to make sure that you can hear me and you can see the slides that I'm sharing. Yeah, good, cool. All right, so we started talking about fluids by defining some properties that all fluids have, like density, pressure, and buoyancy or buoyant force. So all fluids will have those properties, and we can calculate the density, the pressure, and the buoyancy of the fluids. So that was our very first lecture. And so regardless of whether the fluid is stationary or the fluid is moving, it will have density, pressure, and buoyancy or buoyant force. All right. And then in the previous lecture, in lecture 13, we then looked at how we can describe a fluid when it flows, right? So we looked at fluid flow. And so we said that when the fluid flows, we can describe its flow by looking at the flow rate Q. And the flow rate Q is related to the volume of fluid that's flowing across a surface per unit time. And so that fluid flow is also related to the cross-sectional area of where that fluid is flowing times the speed of flow. And then we learned, related to fluid flow, is that the amount of fluid that goes into a certain cross-sectional area should be the same amount of fluid that goes out of another cross-sectional area. And that's the idea behind the continuity equation, which relates how fast a fluid flows across different cross-sectional areas. And then finally, we looked at how pressure P and the speed and the elevation of the fluid are interrelated with each other. So the first lecture, these are general concepts. They refer to all kinds of fluids, regardless of whether the fluid is stationary or moving. Lecture 13, the topics we learned there and these equations, these are also general concepts and general equations that can be used for any kind of fluid that is flowing, right? So in the previous lecture, we did not really distinguish between different kinds of fluids when we were talking about flow rate and continuity equation and Bernoulli's equation. So these concepts and these equations can be used to describe the flow of any kind of fluid, whether the fluid is viscous or not. So we did not distinguish between viscous and non-viscous fluids. And so this lecture today deals exactly with the difference in fluid flow depending on the type of fluid. So we will specifically look at how fluid flow is affected by the viscosity of the fluid. So of course, we will first define what is viscosity, and from there we will be able to distinguish the difference between a viscous and non-viscous fluid. So after defining viscosity, we can look more deeply at a mathematical relationship that describes viscosity that will enable us to see how viscosity will affect fluid flow. And to do that, we'll have to review what we learned in lecture 11 about stress and strain, but particularly shear stress and strain. And from there, once we have a good grasp of what viscosity is, we can then now look at how viscosity affects fluid flow. And this is given by what is called Poiseuille's law. It's yeah, this word is really quite tricky. Yeah, but I checked Google. Poiseuille's law is a French French scientist who investigated viscous flow. And then to wrap up our discussion on fluids, we will look at two kinds of flow: turbulent flow and laminar flow, and see what are the conditions for getting these types of flow. Right? Okay, so let's first define viscosity. So we'll first look at a conceptual definition of viscosity to sort of get a conceptual understanding and idea what viscosity is all about. And then after that, we'll look at the mathematical representation, as I mentioned earlier. So viscosity is represented by this fancy letter N, which is a Greek symbol that we call eta. So we call that eta, and that refers to viscosity. It's a property of the fluid, and it measures the resistance of the fluid to flow. It measures the resistance of fluid flow, essentially. In common speak, in common language, it's often referred to as the thickness of a fluid. Okay, so here, have a look at this video, which shows different fluids with different viscosities, and yeah, so I'll just. So can you hear the sound? No, okay. Let me just see what's going on. Just hang on, I just need to sorry, I think I'll just stop the sharing for a moment. Okay. Flow fastest down can you hear the sound this time? Water, dish soap, yep, okay, oil, okay. So honey, let me restart that. Welcome, ladies and gentlemen, to our first ever viscosity games, where we find out which one of our liquids will flow fastest down our ramp of danger. Water, dish soap, vegetable oil, honey, suntan lotion. And in first place, we have water. Second place, vegetable oil. Third place, our dish soap. Fourth place, honey. And it turns out our suntan lotion was very old. Okay, so looking at that video, which do you think? Yeah. Okay, so those are the different fluids that were in the race. So based on that video and maybe an intuition of what viscosity is, which fluid do you think is the most viscous, meaning the fluid with the highest viscosity? Right, so I can see there a response of honey. Any other responses of what you think is the most viscous? Right, okay, so viscosity measures the resistance to flow, or the thickness of the fluid. Yep, so the thicker the fluid is, the more difficult it is to flow, because there is sort of this internal resistance in the fluid that prevents it from flowing. And so among the different liquids, water had the least viscosity. It was less viscous because it flowed faster. Yeah, honey is very viscous. So notice here, it flows very slowly, but suntan lotion, the lotion especially, did not even leave its container. So it's very, very viscous. So in this case, with these different fluids, the lotion would have the highest viscosity, and we say that it's the most viscous among the liquids considered. All right, so the higher the viscosity, the more difficult it is for the fluid to flow, which means you need to exert more force to overcome the internal friction. And we say that the fluid is viscous, or what is often referred to as being thick. Okay, so that's the qualitative description of the viscosity. Now, if we look at how we represent viscosity mathematically, we'll have to go back to shear stress and strain. This viscosity would then be related to how the fluid is deformed, right? Because when the fluid will start to flow, the fluid essentially deforms as it starts to flow. And so to understand mathematically how viscosity affects the deformation of the fluid as it flows, then let's go back to what we learned in lecture 11 about stress and strain. Okay, stress being related to the force that you apply to an object, and strain being related to the corresponding deformation that the object experiences because of the force that, or the stress that you've applied. But in particular, it will be shear stress that will be relevant to fluids. Okay, where shear stress is the kind of stress where the force is exerted parallel to the surface. So a good example is when you put your hand on top of a book, and if you slide your hand towards the right, away from the binding of the book, you are exerting a force that's parallel to the pages of the book. And what you will notice is that the book will start to deform, with the top pages moving forward in the same direction of the force exerted by your hand. Whereas notice that at the bottom, the pages hardly moved at all. So there's little to no movement at the bottom of the book. The bottom is, of course, fixed to the table or the desk, and the desk is sort of providing the counteracting frictional force in the opposite direction of. So you have this counteracting frictional force in the opposite direction of the pushing force of your hand, and that prevents the pages at the bottom of the book from moving forward. You will also see that there's like this gradient in the deformation of the pages of the book, so that the pages closest to the exerted force by the hand move farther compared to the pages lower, closer to the bottom of the book. Okay? And the stress exerted on the book is related to the force that you applied divided by the surface area over which you apply the force. And correspondingly, the deformation of the book is measured in terms of the strain. Okay, and the stress and the strain is related to the Young's modulus. And Young's modulus, we learned before, is a property of the material. Property of the material that tells you how easily the material is deformed, right? So high high Young's modulus means that it's more difficult for the material to deform. Means smaller deformation or smaller strain, which essentially means if your Young's modulus is big, then the strain is small, the deformation is small. Okay, so that's what happens to solids. Okay, you have this shear stress exerted parallel to the surface, and you have these corresponding deformation that you can see in the solid objects. Now, if we apply shear stress and strain to fluids, it's a little bit more difficult to see. I mean, the deformation of the fluid is a little bit more difficult to see because the fluid is sort of like continuous. We don't see the individual particles or molecules making up the fluid, unlike the pages of the book that we can easily see in the previous example. But this cartoon, this cartoon video that I'll show you shortly sort of shows us how the particles or molecules in the fluid behaves if we apply a shear stress on the fluid. So as you watch the video, I'd like you to observe what will happen to the particles or the fluid molecules on top and at the bottom of the fluid. Right, so I'd like you to observe what will happen to the particles around the top part and going down to the bottom. Right, so I'll show this video now, and hopefully the sound will work this time.
Imagine a boat is moving on water. With boat, water molecules on top layer are also moving.
All right, I hope you heard the sound all right. Was the sound? Yep, okay, good. Yeah, so and I also hope that you were able to observe let's do that again. Yeah, and I also hope that you were able to observe how these particles, these circles represent the molecules, making molecules of the fluids. Okay, notice the boat there is applying sort of the shear stress. So you have a force that's being applied parallel to the surface of the fluid. So that's giving you the shear stress. Okay, which causes the movement of the particles, essentially giving the deformation of the fluid. So let me just play that once again for those who were not able to observe that phenomenon, and then we'll discuss it more closely.
Imagine a boat is moving on water. With boat, water molecules on top layer are also moving.
Okay, so notice so if we look at a particular reference point, so say if we look at this, let me choose a different reference point. So if we look at this reference point and let's see how the particles moved with respect to that reference point. So say, let me try to make that straighter. Yeah. So say, let's say this is the line where the particles are supposed to be aligned before you applied the shear stress. Okay, you have, of course, the force to the right, giving you the shear stress. Okay, and this is our reference point. So notice that on top, close to where the shear stress was applied, this particle here moved quite far. So if you look at the displacement of that particle, it was displaced quite far relative to the reference point. And as you go deeper and farther away from where the shear stress was being applied, notice how the displacement becomes smaller and smaller. And at the bottom, the displacement is almost zero or approximately zero. And we say that that particle at the bottom did not move at all. Okay, so the displacement of these water molecules or these water particles was a result of the shear stress, the force that was exerted parallel to the water surface. Now, if we look at the movement or the displacement of the particles over time, then we will be able to say something about the velocity of the particles, right? Recall that velocity from our very first lecture is equal to displacement over time. Right, so in this case, which particle had the biggest velocity, meaning which particle moved fastest? Is it the particle at the top or the particle at the bottom? At the top, right? And hopefully you also saw that in the video animation video. Yeah, the particle at the top moved fastest because it was closest to the shear force. It also had the biggest displacement, and therefore it will have the biggest velocity. And at the bottom, it's sort of like the particle was at rest and it did not move. So you can sort of see this deformation of the fluid if you trace out yeah, the displacement of individual water molecules, you can sort of like this similar behavior in the deformation of the fluid, similar to the deformation of the textbook that we've seen earlier for fluid, for solids, I mean. Okay, so looking at a more idealized experimental setup where you sandwich a fluid between two plates and you move the top plate here. So you have this fluid that's sandwiched between two plates and you move the top plate to the right. You will exactly see a change in the velocity of the fluid depending on where you're looking at. So at the top of the fluid, you have faster velocity, and as you go deeper, the fluid, the velocity decreases. At the point where the plate is stationary, you can say that the velocity is zero at that point. Okay, so here, hopefully the key idea I wanted to show and to illustrate here in this slide is that when you apply a shear force on the fluid will also sort of deform in this manner, and the deformation is represented by the displacement of the individual water or fluid molecules, and that deformation is related to the velocity of the movement of the fluids, because displacement is related to velocity by dividing it by time. So if we now make a mathematical equation that describes viscosity, then we have the strain, the shear strain, which describes the deformation. The deformation will be related to the displacement over time. Okay? And displacement over time is just the velocity of the particles. And it should also be related to the length or the position of the molecule. So notice here, the length This is the length that we are talking about. And notice that the deformation depends on the position relative to where the shear stress was exerted. So at the top part, you'll have bigger deformation. At the bottom part, where L is bigger, you have almost no deformation. So the shear strain, which describes the deformation, should also be related to the depth of where you're looking at the strain, and of course how fast the molecules are moving, because then that describes the displacement of the particles. Okay, so that's the deformation, and viscosity is defined as the shear stress over shear strain. So looking at analogies, Young's modulus describes how easily the solid object deforms. Okay? For fluids, it's viscosity that defines how easily the fluid deforms, and therefore viscosity defines how easily the fluid flows. Okay? And that is described by the shear stress divided by the shear strain. Stress is, of course, force divided by area, and strain is, as we've seen here, is equal to velocity over length. Okay, we will really just look at, we won't look more closely into the direction, so we can just use speed instead of velocity to describe the strain of the fluid. Okay, and just to complete the discussion for viscosity, the SI unit for viscosity is pascals divided by seconds. It's sort of a strange unit, but force, the unit for force is newtons, divided by the unit of area is meters squared, divided by the unit of speed is meters per second squared, divided by the length is meters. This will work out to be pascals. So on top here is pascals. Yeah, and then it will work out to be seconds there. So this equation can be rearranged. You mean this equation for viscosity? Yes, this equation can be rearranged, and we will do that in the next slide. You can, of course, write this, yeah, because it's quite weird to have all those divide signs. So you can write this also maybe in a neater form. Force times length divided by velocity, or just speed times area. So this will be a simplified form for viscosity if you want to rearrange, if you want to remove like this divide signs on top and below of the divide signs. It was written this way just to show, because shear stress is force over area and shear strain is equal to velocity over length. But of course, I think, yeah, I think you're right. This is a much simpler equation to deal with. Yeah, so yeah, use this equation for viscosity. So if it was Pascal divided by second, oh, sorry, I have, so the unit for velocities should just be meters per second, not meters per second square. So let's try to work out. Yeah, okay, so newtons per meter squared, this one is already pressure, that's equal to pascals. And then you have here, yeah, so this is where it's tricky now when you're doing this divide signs in both the numerator denominator of a division as well. This one, the meters will actually cancel out, and the seconds is in the bottom of the divide sign, so that will actually go up. I think it will be easier to work out the units looking at this rearranged simplified form for viscosity. So if we look at the units from here, so force is newtons, length is meters, so times meters, divided by speed is meters second to the -1, or meters per second, and the area is meters squared. Okay, so looking at this, so this meter will cancel out. Okay, and then you have Newton divided by meter, that's pascals. Newton divided by meter squared is pascals. So that Newton divided by meter squared is pascals. And then you have this second to the -1 here. So if that will go up, yeah, that will be pascals times 7. Yeah, so it's like pascals times seconds. So that's why it's a little, it looks like a strange unit. It's pascals times times seconds for the unit of viscosity. Right? Okay, so we have that equation for viscosity. Now, if based on viscosity, we can classify fluids into two. We can classify them as non-Newtonian fluids and Newtonian fluids. In Newtonian fluids, the viscosity changes with stress and strain. So this means that because the viscosity changes, it means that the fluid will thicken or can thicken or can become more viscous, or the fluid can thin out or can become less viscous when stress or when force is applied to it. And a good example of that is when when you're baking and you mix flour or cornstarch with water. Okay, initially when you mix flour and cornstarch together, you start from a thin fluid, but as you continuously mix it together, then that mixture starts to thicken, and that's because as you mix, you're applying more stress to the mixture, and that changes the viscosity of the mixture, making it more thick. So it's also when you make slime. Yeah, I do that often with my daughter. So you have to make homemade slime. You have glue and dishwashing soap. So if you mix those two together, initially it's quite runny and liquidy, but as you continue to stir and mix them together, then the slime becomes to form, and it becomes thicker, becomes more viscous, and that's a result of the stress that was introduced by mixing continuously. So that's the idea behind non-Newtonian fluids. Their viscosity changes. Okay, for the case of cornstarch and slime, the viscosity increases as they become more viscous when stress is applied. For the example of thinning out, or the fluid becoming less viscous as you apply stress, that's the idea behind quicksand, right? So they say that if you encounter quicksand, for example, you stepped on the quicksand, the best thing you can do is to stay stationary, right? So you probably heard that if you struggle and try to move about to get yourself out, then you'll be in more trouble, because it will be more difficult for you to get out the more you struggle. And that's because quicksand is non-Newtonian. The more it's stressed, the more you struggle and apply force and stress to it, the more it thins out, and the more you sink into quicksand. Okay, for non-Newtonian fluids, the viscosity does not change regardless of whether you keep mixing it, or regardless of whether you continue introducing stress to the Newtonian fluids. Actually, Newtonian fluids are ideal. There's in real life, there really isn't any Newtonian fluid, but to a good approximation, air and water can sort of be approximated to be Newtonian fluids. So yeah, but I think, yeah, I think in this course we'll just mostly deal with we'll approximate fluids to be Newtonian, so that the viscosity does not change, and the viscosity can be considered to be constant. Right, so let's look more closely at how viscosity will affect fluid flow. Um, Viscosity, this was the definition. We can rearrange it as well, and also simplify the equation. And the goal of rearranging this is to see how the viscosity affects the fluid flow in terms of the force you need to apply to make the fluid flow, as well as the speed of fluid flow. So by rearranging the equation for viscosity this way, so that you have a relationship between force and the viscosity eta, we can see a direct proportionality between force and viscosity. Okay, which means that, you know, again, direct proportionality, we've learned this before, means that if something increases, the other thing should also increase, which means that if viscosity increases, then force should also increase. Okay, the more viscous the fluid is, the more force is needed. Okay? The thicker the fluid is, the more force it's needed to cause it to flow. And maybe a good example of this is maybe lotion, or let's say tomato sauce. Okay? Tomato sauce in a bottle. Sometimes you squeeze the end of the bottle, right? Tomato sauce is quite thick, and sometimes so you have to squeeze the bottle in order for the tomato sauce to flow out of the bottle. You have to like exert this force, and the thicker the sauce is, the more you need to squeeze, so that you overcome the viscosity or the thickness of the tomato sauce, and it will cause the tomato sauce to flow. Right, so the force you need to apply is directly proportional to the viscosity of the fluid. So likewise, the speed of fluid flow is directly proportional to the force, which probably makes sense, because, right, the faster, the more you pull on this top plate, for example, then the faster the water molecules on top will move. Yeah. So I think hopefully this relationship between force and speed is rather logical. The more you push, the faster the flow will be. Right, so then we've learned about viscosity. We've seen what viscosity is and how it's related to the force and the flow of the fluids. So for non-viscous fluids, the fluids can flow uniformly. So it's very thin. So there's not a lot of internal resistance in the fluid. So the fluid sort of flows uniformly with a uniform speed um, throughout the fluid. But for a viscous fluid, the velocity is non-uniform. If we look at, so what we looked at here is one plate is moving. Okay, just the top plate is moving and the bottom plate is stationary. And we've seen with the cartoon or the illustration of the boat and the water molecules that the fluid on top will flow faster and the fluid at the bottom sort of is close to stationary. It's not moving because the bottom is stationary. Now in fluid flow through a pipe, okay, it's like you have two stationary plates on top and at the bottom. Okay, so if we do the same analysis that we did previously with a single moving plate, okay, so the water or fluid molecules near the stationary plates will sort of be stationary, so they have zero velocity, and they will be stationary. They're sort of they will probably move, but only just a little bit. But the fluid at the middle will have a faster or a bigger velocity. That's where the force is also being applied close to the middle of the pipe where the fluid is flowing. So if you look at the profile of the velocity, so at the middle you have this fast velocity, and it's tapering down to almost zero velocity near the stationary plates. So for viscous fluids, you have this non-uniform distribution of velocity. Okay, we also seen with the tomato sauce example that I described earlier, that for viscous fluids to flow, you will sort of have to apply some sort of pressure to overcome the viscosity and cause the fluid to flow. So this is governed by Poiseuille's law. So Poiseuille's law says that you need to have a pressure difference between 2 points to cause the fluid to flow. And Poiseuille's equation is given here. It describes the flow rate. Q still refers to the flow rate of the fluid, but it now depends on the pressure difference. So P1 minus P2, that's the pressure difference between 2 points in the fluid. So R, it's the radius of the pipe where the pipe is flowing. It's easy to imagine that. Bigger pipe will have more fluid can flow through it, so you'll have a higher flow rate. We've also seen that last time. Viscosity is here, so that means fluid flow is inversely proportional to the viscosity, and we've been discussing that. The thicker the fluid is, the less likely it is to flow, so it will have a smaller flow rate the bigger the viscosity is. Also, the longer the pipe is, the smaller the fluid flow. Okay, so length is inversely proportional to the fluid flow or the flow rate. And of course, you have pressure there. Yeah, so if it's easier for you, you can also rearrange this equation to be pi r to the 4 multiplied with P1 minus P2 divided by 8 eta times L. Maybe this form of the equation will make it easier for you to rearrange Poiseuille's equation. For example, if you wanted to find P1 minus P2, these equations are equivalent. Okay, so let's look at an example of how we apply Poiseuille's equation and how viscous fluids flow. So drug is delivered to a patient via syringe that is 5 cm long and with an internal diameter of 1 millimeter. And the drug is being delivered at a rate of 10 milliliters per minute. We want to find the flow rate of the drug if the viscosity is 8.9 times 10 to the minus 4 pascals times seconds. And we want to find the pressure in the syringe. The pressure here, essentially P2. Okay, let's assume that it's a Newtonian fluid, so the viscosity is constant. It does not change. So determining the flow rate, okay, we've seen this equation for flow rate for viscous fluids. You sort of need a lot of information to find the flow rate using this equation. For one, you need to know the pressure difference P1 minus P2. But in fact, you don't know the pressure difference, but because that's being asked in the second question. So what should we use to determine flow rate? Can we determine flow rate? Well, I put an answer there, so it means it should be possible to determine the flow rate here. Okay, but how do we determine the flow rate? What is the flow rate? Okay, so the concepts, so as I mentioned in the beginning of the lecture, the concepts we learned in lecture 12 and lecture 13, you can use those concepts even if the fluid is viscous, because those are general concepts that apply to all fluids. Okay, so the definition of flow rate is the volume of fluid flowing per unit time, right? Which is volume divided by time, which in fact is already given in the problem, 10 milliliters per minute. So liters is a unit for volume. Milli is just the prefix 10 to the minus 3. So this milli means 10 to the minus 3, the prefix milli. And then the time is also, so every minute, 10 milliliters of drug is being delivered. So that's essentially the flow rate. It was already given, except that it's not in SI units. So all you have to do is to convert the units to SI units. So convert milliliters to cubic meters for volume. 1 liter is 10 to the minus 3 meter cube, as we've seen in the previous lecture. That's the conversion factor you need. Milli, of course, this is the prefix milli, which is equal to 10 to the minus 3. So you have 10 milli is 10 times 10 to the minus 3. So that's 10 milli, and then 1 liter. Using your conversion factor, you can replace 1 liter with 10 to the minus 3 cubic meters. And so you have the conversion from 10 milliliters to cubic meters here. And of course, for the time, 1 minute is equal to 60 seconds. So substituting the numbers there, you'll have a flow rate in cubic meters per second, as shown here. All right. Are we happy with that? Any questions? Okay, are we happy with the solution for the flow rates of the drug? Yep, good. Okay, second question, find the required pressure in the syringe. Okay, so the reason why you push on the syringe is to apply a pressure across those 2 points. You have the pressure in the syringe and the pressure on the arm. Okay, the pressure will be different because of course you have the blood pressure that you're considering in the arm there. So using Posey's equation, that's where pressure comes in, right? You need to apply a pressure difference for flow to occur. Okay, so we want pressure difference, so we rearrange this equation. So P1 minus P2, it's being multiplied with this whole pi R4. So we just divide both sides, pi R4, pi R4. Okay. And then it's P1 minus P2 is being divided by 8 eta times L. So we multiply by 8 eta times L both sides. And we have this rearranged equation for P1 minus P2. And we know everything. Okay? The length is given 5 centimeters. Everything should be in base units. So it should be converted to meters. The flow rate, Q, we've solved that from the previous question. The viscosity eta is given here. It's already in base units. And then the radius, the diameter is given as 1 millimeter and radius is half the diameter. Therefore, radius is is 0.5 millimeters, but convert that to meters by dividing by 1,000. And so you have 0.0005 meters for the radius. So you have everything. Just be careful that the radius is raised to the power 4. Okay, it's easy to lose that when you're putting numbers in your calculator, so just be aware of that. So you'll have this pressure difference to be about 300 pascals. Right? Okay. Any question about the solution, or are we happy to move on? Yep, good. Okay, so Poiseuille's equation, that's only applicable for viscous fluids. Now, when fluids flow, when fluids flow, they can either behave in a certain way, depending on how fast they flow. And so we can classify flow as laminar or turbulent, depending on how fast the fluid is flowing and how the fluid behaves, the fluid molecules behave while they're flowing. So in laminar flow, as shown in the top figure here, notice how the streamlines are ordered and they're sort of directed towards a single direction. Okay, so the streamlines are ordered, and therefore the pressure, the density, and the flow velocity of the fluid is the same at every point. And we can only have laminar flow if the fluid flows at a low speed. For example, here, when the stream is flowing calmly, then you say that that's a laminar flow. Turbulent flow, for example, is what you observe when you have a waterfalls, for example, so that you have this more complicated orientation of the fluid molecules as they flow. So the streamlines become more irregular and they form vortex-like features, vortices, or whirlpool-like features, for example, when you have rapids or water flows. So it all depends on how fast the fluid is flowing, whether you have laminar or turbulent flow. The question is, what's the reference speed, right? Okay, so when we say turbulent flow occurs when fluid flows fast, okay, how fast is fast? How fast is fast is defined by the Reynolds number RE. So Reynolds number R subscript E gives you the flow rate for when turbulent flow occurs. And it depends on these variables. If it's easier for you, also you can write down Reynolds number as density times diameter times flow rate divided by the area times the flow rate. So I'm just checking if I actually have should have a slide with definition. So rho, that's the density of the fluid that's flowing. D is the diameter diameter of the pipe where the fluid is flowing. A is the cross-sectional area. Eta is, of course, the viscosity, and Q is the flow rate. Okay. So flow rate, that's A times B. So that's where the speed comes in when determining whether you have turbulent or laminar flow. And if the Reynolds number is greater than 3,000, that will give you turbulent flow. If the Reynolds number is less than 2,000, that will give you laminar flow. So there's a little bit of a gap between 2,000 and 3,000. That's sort of like the transition region where you have interchanging turbulent and laminar flow. So to determine whether the flow is turbulent or laminar, you'll have to calculate for the Reynolds number given these parameters here. Right. Let's look at an example okay, so let me just see, there's a question. Okay, so can a syringe question use Bernoulli's equation if it's not a viscous fluid? The answer is yes. So you can use Bernoulli's equation. Bernoulli's equation can be used for viscous and non-viscous fluids. But for Posey's equation, it's you can only just use Posey's equation for viscous fluids. You cannot apply, meaning you cannot apply Posey's equation for non-viscous fluids, right? We will not specify which equation you need to use. I think it's part of the what's being tested in the question, but you can sort of deduce what equation to use based on what information we will give you. So if we will if the question requires you to use Posey's equation, we will definitely give you the viscosity eta, because Posey's equation depends on viscosity eta. So that's a clue that you can use. If we give you the viscosity eta, then that means we want you to use Posey's equation. Or if we give you the length of the pipe, then that's also a key clue that you should use Posey's equation. Note that the viscosity and the length L, they are not in Bernoulli's equation. So can can we use Bernoulli's for viscous fluid? Yes, Bernoulli's equation is also valid for viscous fluids because Bernoulli's equation relates pressure, speed, and elevation. So if you think about a viscous fluid, if you change the elevation, then the pressure would also change, right? And the difference in pressure will cause the fluid to flow. So like the video of the competition between the different kinds of fluids flowing down the ramp, okay, you're actually having a different elevation at different points of the ramp for the fluid to flow. So you have here a change in elevation. You also have there a change in speed between 2 points in the ramp. And you have there the density of the fluid. So thinking about that, you can then use Bernoulli's equation for honey to analyze the flow of honey down the ramp, for example. Yeah. So Bernoulli's equation is a general equation that can be used for any kind of fluid, but Posey's equation is only specific to viscous fluids. Yeah, I hope that makes sense more. Yep, okay, good. All right, so turbulent and laminar flow. let's look at an example of the types of questions relating to Reynolds number and turbulent and laminar flow. So in the previous example for the drug delivery, we want to determine whether the flow of the drug is turbulent or laminar. If the density of the drug is 1050 kilograms per cubic meter. So from the previous example, we already solved for the flow rates of the drug out of the syringe. The diameter of the syringe was also given in the previous scenario, previous example, and then the viscosity of the drug was also given. And then there's a follow-up question here. Okay, what will happen if the flow rate is increased? But first, let's look at the first question with the previous parameters. Yeah, I've already written it down here. Let's determine whether the flow is laminar or turbulent. A Reynolds number is this equation: density times diameter times the flow rate divided by the cross-sectional area times the viscosity. So area, we can assume that the syringe is a cylinder. So if you cut through the syringe and look at one end, you'll see a cross-sectional area, a cross-sectional shape of a circle. And the area of that circle is pi r squared. Okay, so the radius is half the diameter. Okay, remember to convert that to meters. So 0.001 meters for the diameter. Halve that will give you the radius. So it's 0.005 for the radius squared, giving you this area right here. So we know everything is just a matter of substituting. So the density of the drug times the diameter of the syringe, it has to be in meters, so everything should be in base units. The flow rate divided by the cross-sectional area multiplied with the viscosity. It gives you a Reynolds number of 251. So do you think the flow is turbulent or laminar? Yeah, laminar. So it's really just comparing the Reynolds number that you've obtained to the criteria for turbulent and laminar flow. So for turbulent flow, that's when you have Reynolds number more than 3000. Okay, the Reynolds number is less than 2000, so that will be a laminar flow. So if the flow rate is increased to 250 milliliters per minute, so that means that's a factor of 25, because originally the flow rate was 10 milliliters per minute, right? We just converted milliliters to meter cube and then minutes to seconds, but originally the flow rate was 10 milliliters per minute. So if you increase it to 250 milliliters per minute, then that's a factor of 25. You've increased the flow rate by a factor of 25. So how will the Reynolds number change? So do you think it will still be laminar or turbulent? So the Reynolds number when the flow rate was 10 was 251. Do you think it will be laminar or turbulent flow if we increase Q by a factor of 25? Right, turbulent, good. So we need to figure out what the new Reynolds number is. So from the previous question, Reynolds number is 25. Q increases 25 times. Notice how Q is directly proportional to the Reynolds number, right? So if Q is doubled, the Reynolds number should also double. in this case, Q is 25 times bigger than before. So the Reynolds number should be 25 times bigger than before. Yeah. Yeah, so turbulent, good. You need to do the equation. So you either do this equation, again, substituting density, diameter, the new Q, divided by area times M, or you can use the previous Reynolds number you got, 251, and increase that by a factor of 25, or multiply that by 25. Then you then see that the Reynolds number is more than 3,000, therefore it will be turbulent flow. Okay. Yeah. So it's really just determining Reynolds number and comparing it to the criteria for turbulent flow. So since Q is on top, means that it's directly proportional to the Reynolds number. 6 to 90, it's quite close to the new Reynolds number. So maybe it's just a rounding. Is it just a rounding thing? So if you, let me just double check that. 251. 251 times 25 does give you 6275. So I wonder if it's just a rounding thing. 1.67 times 8.9. Yeah, so multiply 25 with 251. This one. Or which Q? So Q from the original Q. So 10 milliliters. Oh, okay. So if you multiply the original Q by 25, then you also still have to, yeah, I think it's just the rounding of Q. So it's the rounding of Q there, that when you multiply that with 25, the rounding error increases. And then you still need to multiply that with density, multiply that with the diameter, and then divide that with, okay. So you got it. So it's just a rounding error, but what you got is actually quite close to the answer. 6275 is close to 6290. So that's why it's just a rounding. In the test or exam, it shouldn't be a problem. Rounding shouldn't be a problem, because if it's multiple choice, we will give you numbers that are very far from each other, and rounding errors shouldn't affect the correct answer. Yeah. Okay, so there's here a question from Moore. If it's on top, is that directly proportional, and multiply, is it inversely proportional? So if it's on top, so Reynolds number, like this. Okay, so it's all a matter of, it's implied that if you have a variable that's written just by itself, that is divided by 1, but we don't write the divided by 1 anymore, because anything you divide by 1 is the same as itself, right? So that means if you write the Reynolds RE on the left in the same form as the equation on the right, then the equation will look like this, strictly speaking. You have RE divided by 1. That means you compare, if you're doing direct proportionality or inverse proportionality, you're comparing like the quantities on top with the quantity on top on the left with the quantity on top on the right, see? So this is direct proportionality, okay, because they are both on top of the denominator sign. So that means density is directly proportional to Reynolds, diameter is directly proportional to RE, and Q is directly proportional to RE. So yeah, and then A and N, they're inversely proportional. So these things here, inversely proportional to the Reynolds number, and these ones here on top are directly proportional. So yeah, so if you swapped A times eta for Reynolds, that, oh, okay. So yeah, you're right. So if you swap that, you're right. If you swap A eta rho dq over Reynolds, if you swap that, it becomes like that. But when you're comparing two quantities and saying directly proportional, inversely proportional, those two quantities should be at opposite sides of the equal sign. Okay. So we can only conclude direct or inverse proportionality between quantities that are at opposite sides of the equal sign. So in this case, it should be the equation should be in this form, so that Reynolds is in one side and Q is on the other side of the equal sign. If we put the two quantities in the same side of the equal sign, then it's hard to see what will happen, because the effect will cancel each other out. Yeah, and it's hard to see what will happen if you increase Q. Then what you can solve is actually A times N, if that makes sense. With the second equation here, what we are solving is A times N and not the Reynolds number. So it's hard to see what will happen to the Reynolds number if you change any of this density D or Q. Okay, so when you're comparing direct or inverse proportionality, the two quantities should be at opposite sides of the equal sign, so that if you change Q, for example, then you will be able to solve for Reynolds number. Yeah, I hope that's clear. I'm not sure if that makes sense more. So direct proportional means Reynolds goes up, then rho d goes up. Yes, yeah. So direct proportional means Reynolds goes up if rho times d times q will go up. And yeah, that's right. And rho dq goes up when eta goes down, and vice versa. Yeah, you're right. So I think you got the idea there. All right. Okay. So let's yeah, think just so in this example, the Reynolds number is more than 3,000, so that will be a turbulent flow. Oh yeah, and that's the end of the lecture. Yeah, okay. All right. So that's the end of the lecture on viscous fluids. We first define what viscosity is, and then we tried to look at the mathematical representation of viscosity, and from there we were able to see how viscosity affects fluid flow. Um, and Posey's equation tells us that for a viscous fluid to flow, there has to be a pressure difference, essentially providing that force that will push the viscous fluids and cause it to flow. And The kind of flow depends on the Reynolds number. Calculating what the Reynolds number is and comparing it to the criteria for turbulent flow, which is greater than 3000 Reynolds number, and laminar flow, which is less than 2000 Reynolds number. Okay, so that wraps up our discussion on fluids. The workshop, so feel free to type in if you have any questions regarding fluids. I'll keep the annotations and post that onto stream later on. But the workshop 14 relates to viscous fluids, what we've just been talking about. So I'll give you some time to look at workshop 14 and start working through the problems. Of course, if you have any questions while we're working through the problems, feel free to put them in the chat box. I'll still be here monitoring the chat. Maybe let's meet again, say, how about at 11:30? Do you think it's just 15 minutes? Okay, 11:30. Let's meet again at 11:30, and let's look at solutions to the workshop problems. I won't end the Zoom session, so you stay here, but I'll just end the recording.